Welcome to this comprehensive guide on implementing timers and countdowns in your C# projects, specifically within Visual Studio and the Unity 3D game engine. This tutorial is designed for beginners, providing a step-by-step approach to mastering these essential time-based functionalities. We will explore various methods and best practices to ensure your applications and games are dynamic and responsive. Understanding how to manage time-based events is crucial for creating dynamic and interactive applications, from intricate game mechanics to responsive user interface elements. Proper timer implementation ensures smooth execution of delayed actions, periodic updates, and precise event scheduling, which are fundamental to modern software development. We'll start by exploring the fundamental concepts of timers in C# using Visual Studio, laying a strong foundation for more complex implementations. This initial section will cover the core principles and different types of timers available in the .NET framework, providing you with the knowledge to choose the right tool for your specific needs. Our first method involves using the system threading timer class, which is ideal for executing a method at regular intervals on a thread pool thread. This timer is lightweight and efficient, making it suitable for background operations that do not require interaction with the user interface. It operates independently of the main application thread, preventing UI freezes. Here, we define a callback method that the timer will invoke. This method will contain the logic you want to execute periodically, such as updating data, performing calculations, or logging information. The timer callback delegate ensures that the method signature matches what the timer expects, allowing for seamless integration. Next, we instantiate the timer, passing our callback method, an optional state object, the initial delay before the first invocation, and the interval between subsequent invocations. The initial delay and interval are specified in milliseconds, giving you precise control over the timer's behavior. For example, setting the initial delay to 0 means the timer starts immediately. Remember, the system threading timer is non-blocking, meaning it won't halt your main application thread, making it suitable for background tasks. This characteristic is vital for maintaining application responsiveness, especially in desktop applications or server-side processes where UI interaction or continuous operation is critical. It leverages the thread pool to manage its execution. Another powerful option is system timers timer, which raises an event at specified intervals and can be configured to run on the UI thread if needed. This timer is more feature-rich than system threading timer, offering properties like auto-reset and synchronizing object for greater control over its behavior and thread affinity. It's often preferred for applications that need to update UI elements. To use this, you'll subscribe to its elapsed event. This event handler will contain the code that executes each time the timer interval passes. By subscribing to the event, you can cleanly separate your timer logic from the timer's configuration, making your code more modular and easier to maintain. The elapsed event args provides information about the event. You can set the interval property in milliseconds and then call start to begin the timer. The auto reset property determines if the event is raised repeatedly or only once. If auto reset is set to false, the timer will fire its elapsed event only once after the specified interval, then stop. Setting it to true makes it a recurring timer. For UI-specific applications, System, Windows, Forms, Timer or System, Windows, threading that dispatcher timer are excellent choices as they operate directly on the UI thread. These timers are specifically designed to interact with UI elements safely, preventing cross-thread operation exceptions that can occur when background threads try to update the UI. They simplify UI updates by marshalling calls to the UI thread automatically. Now, let's transition to implementing countdowns, which are essentially timers that count down from a specific value to 0. Countdowns are ubiquitous in applications, from game mechanics like bomb defusal timers to user interface elements indicating remaining time for a task or offer. Understanding their implementation is key to creating engaging user experiences. A simple countdown can be achieved by using any of the timer types we've discussed and decrementing a counter variable in the timer's callback or event handler. You would initialize an integer or float variable with the total countdown duration, and each time the timer ticks, you subtract the elapsed time or a fixed unit, like 1 second, from this variable. When the counter reaches 0, you can stop the timer and execute your desired countdown finished logic. This logic might involve displaying a message, triggering an event, or enabling a new functionality. It's crucial to ensure the timer is stopped to prevent unnecessary resource consumption and to clearly signal the end of the countdown period. Moving into Unity 3D, the approach to timers and countdowns differs due to its game loop and mono-behavior lifecycle. Unity's execution model is frame-based, meaning operations are typically performed once per frame, which requires a different mindset compared to traditional C# applications. Understanding this distinction is vital for effective game development. The most common way to handle time in Unity is through coroutines or by using the update method with time.deltaTime. Both methods offer distinct advantages depending on the complexity and nature of the time-based event you wish to implement. Coroutines are excellent for sequential, time-delayed operations, while update is suitable for continuous, frame-by-frame logic. Let's start with time.deltaTime. This property returns the time in seconds it took to complete the last frame, allowing for frame rate independent calculations. By using time.deltaTime, your timers and movements will behave consistently across different machines, regardless of their processing power or frame rate, which is a cornerstone of robust game development. To create a timer, you'll accumulate time.deltaTime in a float variable. When this variable exceeds a target duration, your timed event occurs. After the event, you typically reset the accumulator to 0 to start the timer again, or you can stop accumulating if it's a one-shot timer. This pattern is fundamental for implementing cooldowns, delays, and periodic events in Unity. For countdowns, you initialize a float variable with your desired countdown duration and then subtract time.deltaTime each frame. This continuously reduces the remaining time until it reaches 0. This method provides a smooth and accurate countdown that is synchronized with the game's frame rate, ensuring precise timing for game events. When the countdown variable drops to 0 or below, the countdown has finished and you can trigger your end of countdown logic. This could involve activating a game over screen, spawning an enemy, or enabling a player ability. It's good practice to ensure the countdown variable doesn't go significantly negative by clamping it at 0 after the event. Coroutines offer a more readable and sequential way to handle time-based operations, especially for delays and sequences of events. They allow you to write asynchronous code that appears synchronous, making complex timed sequences much easier to manage and understand. This is particularly useful for animations, spell casting, or multi-stage events. You define a coroutine as an IEnumerator method. Inside, you can use yield_return_new wait for seconds to pause execution for a specified time without blocking the main thread. This allows other game logic to continue running while the coroutine waits, making it highly efficient for managing delays and staggered events within your game. To start a coroutine, you call startCoroutine and pass the coroutine method. This allows the method to run over multiple frames, executing parts of its logic, pausing, and then resuming later. You can also stop a running coroutine using stopCoroutine if its conditions change or the event is no longer needed, providing flexible control over timed sequences. For countdowns with coroutines, you can loop, decrementing a variable and yielding for 1 second in each iteration until the counter reaches 0. This creates a clear, step-by-step countdown that is easy to read and debug. For example, you might have a while loop that continues as long as the countdown time is greater than 0, updating a UI element and then waiting for a second. A helpful tip for Unity is to use time.timescale to pause or slow down all time-dependent operations in your game, including timers and animations. Setting time.timescale to 0 effectively pauses the entire game, while values between 0 and 1 can create slow-motion effects. This global control is incredibly useful for pause menus, cinematic sequences, or debugging. Another tip, when displaying countdowns in the UI, ensure you format the time correctly, often converting seconds into minutes and seconds for better readability. Players expect to see 130 rather than 90 seconds. This involves simple mathematical operations to convert total seconds into minutes and remaining seconds, then formatting them into a user-friendly string. Always consider edge cases, such as what happens if a timer is stopped prematurely or if the game state changes unexpectedly. Robust timer implementations include checks and safeguards to handle these scenarios gracefully, preventing errors or unexpected behavior. For instance, ensure that any resources allocated by a timer are properly released if it's stopped early. For more advanced scenarios, consider using third-party libraries or custom timer managers to centralize and simplify your time-based logic. These solutions often provide additional features like pooling timers, managing multiple timers efficiently, or offering more complex scheduling options. This can significantly reduce boilerplate code and improve the maintainability of your project. Remember to choose the right timer mechanism for your specific needs, balancing performance, readability, and integration with your application's architecture. Each timer type has its strengths and weaknesses, and selecting the most appropriate one will lead to more efficient and maintainable code. Consider the context. Is it a UI update, a background task, or a game mechanic? By mastering these techniques, you'll be well equipped to implement robust and responsive time-based features in both your Visual Studio and Unity 3D projects. From simple delays to complex event sequences, the knowledge gained here will empower you to create more dynamic and engaging applications and games. Practice these concepts to solidify your understanding. Thank you for watching this tutorial. We hope you found it informative and helpful for your development journey. We encourage you to experiment with the different timer types and apply these concepts in your own projects to gain practical experience. Happy coding, and may your timers always be precise.